Yeah, in the record. Yes. Okay. So, good afternoon, everyone. Welcome to ACON's seminars. And and many of you guys already know ACON was launched a year and a half ago with the aim of enhancing collaboration in research and education in the area of autonomous and connected systems. And control, optimization, networks, robotics, and learning are all major themes of ACON. And from a year and a half ago, we started to organize seminars with a theme. And this semester, we have Arbor Fazal and Masha, our seminar organizer. I try to invite, the most international well-known researchers to the seminar at ACON. And today you will see a distinguished guest, and he has done excellent research in this area. I actually checked his website. I see a lot of paper in SML, that perhaps one of the #1 machine learning covers. But I will not tell who it is, and I will let our seminar organizer to formally introduce our guest. So our Fazal, it's yours.
Hi, Xiaoxiao. Yeah, it's certainly our pleasure to have Professor Amin Karbasi as our speaker this week on ICON seminar on control meets learning. Amin Karbasi is currently an associate professor of electrical engineering, computer science, and statistics and data science at Yale. He's also a research scientist at Google, New York. He has been the recipient of several awards for his research achievements in machine learning, statistics, and computational neuroscience. Just to name a few, he's been the recipient of the NSF Career Award, ONR, AFOSR, and DARPA Young Faculty Awards, as well as several research awards and fellowships from AI companies such as Amazon, Google, and Microsoft. He has also received several awards at premier conferences and journals such as AI Stats, ICASP, ACM Sigmetrics, and ISIT. His PhD work received the Patrick Denantes Memorial Prize for the best doctoral thesis from the School of Computer Science at EPFL. So without further ado, I'll let Amin start his talk.
Okay, thank you very much for the very nice introduction, and thank you for inviting me. It is certainly a pleasure to give a talk. I would like to give a talk sometime in the future in person and see your beautiful campus with all sorts of amazing faculty that you have. Unfortunately, we are still in the middle, maybe the end, hopefully, of COVID. So we have to do things online. And today, let me see if it works. Yes. So today I'm going to talk about or motivate my talk about how we should probably run a vaccination trial, or maybe how we shouldn't actually run a medical trial. And more broadly, I'm going to talk about sequential decision making and try to understand how much interaction a policy needs to have with the environment. Okay, so running medical trials was indeed one of the main motivations of Thompson in his seminal work about bandit problems that I'm going to explain later, where he was, at the time he was a member of the pathology department at Yale. Here, let's assume that we have K imaginary vaccines where the efficacy of vaccines are some number between 0 and 1. Of course, a priori, we do not know how efficient the vaccines are. And usually we would like to find out which one has the highest efficacy and so that we can actually apply that vaccine to people. And for that reason, we have to run trials, right, on real people. And that is actually the issue, right? Okay, so first, let's consider the simplest setting, which is the non-interactive setting. And it is usually the one practiced in medical domains and known as randomized trial, where we randomly assign patients to vaccine, right? And we wait some amount of time, say W days, to see which patients develop immunity. Okay, so running such a procedure is simple because we do not need any coordination. It is fast because we see all the results after W days, but it is not efficient in a very important aspect because many patients are not going to get the top vaccine. So we have K vaccines. Say one of them is the top vaccine. Only 1/k fraction on average, 1/k fraction of the patients are going to get the best vaccine. Almost everyone else is not going to get it. Okay, so that is the issue with not being adaptive. So on the other hand, in the interactive setting, maybe the nurse administers the vaccine to patients one by one for the total number of T rounds. We're waiting W days between the rounds to check the efficacy of the previous injections in order to decide which vaccine to use next. So here, basically the nurse is looking at the history and deciding what to do next, right? And by gaining more and more information, maybe over time, we understand which vaccine is better. And then we can basically inject that vaccine. Okay, so right off the bat, we realize that this method is not simple, right? So the nurse faces a dilemma that is called the exploration-exploitation trade-off. So should she explore an option that looks inferior or exploit by going with the option that looks best currently? In other words, based on the history, one of the vaccines may look better than the other ones. So she can greedily pick that one for the remaining patients. However, there might be a vaccine that she has not tested yet that works better than anyone before. So from this aspect, it is better to explore the ones that we have not seen. And this is exactly the dilemma here. On the positive side, if the nurse can solve this dilemma, then maybe many patients will get the top vaccine over time. On the negative side, because this is a fully sequential mechanism, right? At each round for each patient, we look at the full history. It takes a long time. Basically, the number of rounds times the waiting time, T times W, in order to finish this process. So suddenly, from W days in the non-interactive setting, we have, the waiting times becomes T times W because, the nurse should inject the vaccine, wait W days, see the result, and then decide what to do next. Okay, so there are indeed many effective policies that efficiently balance between the exploration and exploitation. And two of the maybe the most well-known ones are the upper confidence bound and the Thompson sampling, which was originally proposed by Thompson as a heuristic method. So today I'm mainly going to talk about these two methods and discuss how they work and then how we can apply them in our setting. Okay, so let's first start with the upper confidence bound. So more abstractly, in a multi-arm bandit problem, which is simply an instance of a two-player game, we have T rounds of interactions between a player and the environment. So player was the nurse, environment was the actions, the reward that we get from the vaccines. Where at each round, an action AT, which is which vaccine, is taken by the player, and only the reward of that action is revealed by the environment. So in our example, if we inject a vaccine to a patient, we only see the result of that vaccine. And we don't get any information about other vaccines. Okay, so that's the bandit feedback. And the goal here is to maximize the the cumulative reward or the overall satisfaction of patients. Right? So that is what we want to maximize. We want to make sure that overall the patients get the the best treatment that we can offer. The issue is that a priori we don't know, and that is the whole exploration exploitation trade-off. Okay, and let me start with the maybe the simplest bandit setting, basically the stochastic multi-arm bandit, where we have a finite number of arms or actions, say K, where each arm is associated with an unknown probability distribution, P, which is supported between 0 and 1. So each action is associated with a probability distribution. And these probability distributions are unknown, okay? And the goal is to, again, maximize the cumulative reward, or equivalently minimize regret, which is a difference between the best fixed action in hindsight and the cumulative reward of the player over T rounds. So in the stochastic multi-arm bandit, the player selects an action at at each round T, and the environment reveals a reward RA sampled independently from P of A. So that is the stochastic part of it. These rewards are sampled independently from these distributions. So in our example, the expected regret would be the difference between injecting the best vaccine in hindsight to all patients and what we actually did in during the whole trial, during T rounds. And clearly, we would like to minimize regret in life and in this problem. And note that because this is a stochastic setting, we are only going to talk about the expected regret, where mu star is the mean value of the best fixed action or vaccine in hindsight. Okay, so is the setting clear? Good, because if this is not clear, the rest of the talk might be hard to follow. So, as I said, the issue is that we do not know these mu's, the mean value of the actions, or otherwise the problem would have been trivial, right? Pick the one that has the highest mean value. So the upper confidence bound algorithm or policy is an optimistic policy that uses the data collected so far to assign to each arm a value that is an overestimate of the unknown means. Okay, so here, T sub I, capital T sub I at time T indicates the number of times the arm I has been played up to time T, and mu hat is the number of time is the empirical mean. So in the beginning, the upper confidence bound of all arms are set to infinity. And once we play the arms, their values or upper confidence bounds are updated as shown here. So the UCB, the upper confidence bound of an arm I at the TS iteration is this is basically its empirical mean plus the confidence interval, which is calculated using standard concentration bounds, such as Hoeffding's. Okay, so for each arm, we are going to assign a value that is shown here. In the beginning, all the values are infinity, very, very large. And then as we play, the values are going to change according to this formula that I'm showing here. So how does the UCB policy work? Well, at each round T, it selects the arm with the highest upper confidence bound in order to efficiently balance between the exploration and exploitation steps. So in fact, it is easy to show that with high probability, 1 minus delta, the mean value cannot be larger than the empirical mean plus the confidence bounds. So note that the first term, the empirical mean, is the exploitation part, which basically means if we don't know which action is best, then choose the one that currently looks to be the best one. Okay. And the second term, the confidence bound, is the exploration term. So effectively, this part of the equation provides a measure of the uncertainty for the action's reward estimate. So if an action hasn't been tried very often, the uncertainty term will be large, making this action more likely to be selected next. In contrast, every time the action is selected, the uncertainty will shrink rapidly, right? Because it is inversely proportional to TI, which is the number of times an action is selected. Okay. So super simple algorithm. So as the time progresses, the exploration term gradually decreases until eventually, actions are selected basically based on the exploitation term, the empirical mean. And formally, given a gap between the mean reward of the best, having a gap between the best arm and the remaining arms, one can show that this UCB policy achieves the tight problem-dependent regret bound that only logarithmically depends on the horizon t. So the regret now is going to be basically O of log t times some constant values. Okay. So for our vaccination problem, here is basically the picture that we have. If we use non-sequential policy, sorry, do you guys actually see the?
No, we cannot see your slides right now. I mean.
Oh, okay.
Now we can see it. Yes.
Now, okay. Okay. So you see the waiting time and the regret.
Yes.
Very good. So for our vaccination policy, here is a picture. If you use a non-sequential policy, then the regret should grow linearly with t. But the waiting time is only W, right? In contrast, if we use UCB, the regret only grows logarithmically with t, but the wait time is t times W. And what we are going to do next is to show how we can achieve almost the best of both worlds. Okay? Good. So to accelerate the process, we would like to treat groups of patients, simultaneously or in parallel, with the data from each batch influencing the design of the next. Right? This way, we only wait W days to see the result of the whole batch. And the way that we can actually parallelize UCB is as follows. So before actually saying that, here we have a more sophisticated dilemma, because we only receive information after all arms in a batch are played, correct? So in order to basically perform such parallelization, we are going to rely on what is called the arm elimination. So in each batch, we explore several arms in parallel. Then at the end of the batch, we eliminate those arms that are that we are certain that are suboptimal, and then repeat, with a batch that has a larger size. So now I'm going to make this actually precise. So more specifically, we keep a set of active arms. So initially, all arms are active. Then in each batch, except the very last, say the jth batch, each active arm is going to be pulled or played q times q to the power j times. And q, we are going to set it to be t, the horizon, to the power 1 over b. And b is the total number of batches. So basically, the player selects an active arm, A, in the jth batch, q to the j times. Then she's going to update the empirical estimate of the mean value and removes any arm that is suboptimal. So what does it mean to be suboptimal? It means that the empirical mean of that arm is significantly below the current best arm by a factor that I'm showing here. It is a square root of 2 times log over 1 over delta divided by Cj. So Cj is the total number of arms pulled by the JS batch. Okay. And for the final batch, the player only selects the best arm. So if we set delta to be basically 1 over k times t times b, then the regret of the batch arm elimination will be bounded by t to the 1 over b times log t times the sum that we saw before. So what does that mean? So here, this is for any number of batches b. Okay, so in particular, if we let the number of batches be basically on the order of log t, then the regret of our batch policy matches the UCB algorithm. Okay, so because t to the 1 over log b is going to be a constant, and this is going to be basically, again, O of log t. So in other words, increasing the number of batches from log t to t does not reduce the expected regret by more than a constant multiplicative factor. And what is even more interesting is that this result is not only tight in terms of regret, but also almost tight in terms of the number of batches. There is a very nice paper by Gao et al. In NeurIPS that basically they show that in order to obtain the optimal problem-dependent regret, what I'm showing here, so basically in order to obtain O of log t times sum of 1 over deltas, any batch algorithm has to have at least log t over log t number of batches. Okay, so with log t number of batches, we get this, this regret, and going below log t is basically very difficult. And among friends, log t is constant. So pictorially, we are going to have basically the following scenario. So our semi-sequential policy achieves the same log t regret, while basically the wait time only increases by a log t factor. Right. So this is somehow, the best of both worlds. Okay. Good. Oops. Can you, okay. I cannot, can you hear me?
We can hear you, but we don't see your slides.
I don't know what happened again. This is, do you see the slides?
Yes, yeah, no,
okay.
No.
Good, okay, yeah. Okay, so I think this is a good part if there are any questions. No? Very good. So now actually let's consider a more practical and richer generalization of the multi-arm bandit, which is the contextual multi-arm bandit. Here at each iteration, the nurse has, still has to choose between K vaccines, but she also sees a D-dimensional feature vector, which is, they're known as the context vector, such as the medical record of the patient, that she can use together with the reward of the, of the vaccine injected in the past to make the choice of the next vaccine. So over time, the nurse's aim is to collect enough information about the context vectors and rewards that are related to each other, so that she can predict the next best arm to play by looking at the feature vectors. So the idea is that these feature vectors are somehow related to the rewards. The nurse doesn't know a priori how they are related, but as she collects more and more information, the hope is that she understands the relationship, so that next time a patient comes with a particular context, like age, blood type, whatever, she can administer the best treatment. And almost all the applications of bandit problems that I know of are of this form. So there is there's some side information about the problem. Okay. So in its simplest form, basically the linear contextual bandit, the reward is related to the context in a linear way. All right. So here we have, so for instance, the reward, if the context is smoking, diabetes, blood pressure, whatever, maybe the reward is like 10 times smoking plus 5 times diabetes or minus 3 times blood pressure. All right. It's a linear relationship. And here we have a set of actions, vaccines to choose from, K of those, and we have an unknown parameter theta star. And the reward is simply the inner product between this unknown parameter times the action or the context plus some sub-Gaussian noise. And the regret is defined, as usual, basically, the difference between what we could have obtained in hindsight by playing the fixed best arm with respect to what we have played over capital T rounds. And this setting clearly generalizes the stochastic multi-arm bandit by, if you choose the context vectors or the actions to be the unit vectors in dimension D, then, we are back to the stochastic multi-arm bandit. So it's a strict generalization of that setting. So now again, we need to generalize the arm elimination strategy in order, to basically remove arms, right? To find what is the best arm over time. There are potentially, infinitely many arms. Here, I'm going to concentrate on the case that are finitely many, K of those. And what we have to do is, find a coarse set construction of arms and build confidence intervals. So the final goal is really to get a good estimate of theta star that we don't know. Once we know what is theta star, then it is easy to select what is the best arm. It's going to be the one that, the inner product between its context and theta star is maximized. Okay. So let's assume that, we have played n arms, A1 through AN, and we receive the rewards, and we have, the sub-Gaussian noise, and mu1 through mu(n), and the assumption is that it is one sub-Gaussian. Now, okay, this is a set of linear equations, so we can estimate, right? There is a least square estimator, theta hat, which can be easily obtained. And then what is nice is that, again, based on concentration bounds, the probability that the inner product between any action, any arm A, and theta hat, our estimator, minus theta star, the correct value, is greater than some ball, some confidence interval, is less than or equal to delta. Okay, so it's a uniform bound, pretty much close to what we need. Okay. So what we really need is that, we need to find the shortest set of actions, because we want to find this, a good estimator of theta star by playing as few actions as possible. So we need to find the shortest set of actions such that with high probability, the inner product between any vector A and theta hat minus theta star is less than epsilon with high probability. That is what we need to do at the end of the day. And it is known that finding, an accurate, approximation, what is the smallest n such that this happens, is a very difficult, intractable problem in integer programming. But finding a good approximation turns out to be efficient for a large class of problems, in particular for linear bandit problems. So how do we find such an n, right? We want to find an upper bound on n. We want this n to be as small as possible. And it turns out that this problem is related to a very famous problem in statistics called the G-optimal design. And I'm going to show next how this is related to G-optimal design problem. So what is the G-optimal design? We would like to find pi. It's a probability distribution, which is called the design, such that G of pi, which I'm showing here, is maximized. Okay. Pictorially, this is an ellipsoid, and we want to basically find the volume of the ellipsoid that is as large as possible. And so V of pi is going to be, just remember it is, these probability distributions, and AA transpose is a matrix, and then each matrix is weighted by pi of A. So this is V of pi. And the maximization is with the norm. So it's the norm of the it's called the matrix norm of the vector A. Okay. So how can we use let's say that we can find the solution to this problem. How can we use it? Let me first show that. So let's say that pi is a design and A is actually in the support of pi. And let's assume that we choose each act. Suppose action A is chosen exactly n sub A times. Okay, so and n sub A is this expression here, which of course relies on the solution of the G-optimal design. And then the matrix V and V pi are going to be, so we can so if choosing action each action A exactly n sub A times ensures that the vector V that we are looking for, and and constructed this way, is going to be related to V of pi. And then which actually means that for any action A with high probability, meaning 1 minus delta, the inner product being less than epsilon is greater or equal to 1 minus delta. Okay, so this is how we are going to use the G-optimal design problem. We get the how many times we have to choose an action, construct a vector v, and then and this vector v is going to give us the confidence bound, which is less than epsilon. Okay, so note that the total number of actions required to ensure a confidence width of no more than epsilon is bounded by exactly this expression that comes from the previous theorem. The question is, what is g of pi? And then there is a very famous theorem called the Kiefer-Wolfowitz theorem that states that for the optimal design, g of pi is going to be d. So basically, this gives us n, right, is going to be bounded by exactly this expression, d over epsilon squared log 1 over delta. So that is basically the shortest number of arms we have to play in order to ensure that with high probability, the inner product is less than epsilon. But it does not tell us, right, that how we can actually find such arms. It tells us this is the number, but how should we choose them? And it turns out, the computation of an optimal design for at least for finite action set is a convex program, for which there are many ways. One way is to use the Frank-Wolf algorithm. So Frank-Wolf is an algorithm in order to solve say convex optimization problems given a convex constraint set. And here the constraint set is basically the simplex of probabilities, such that the algorithm never leaves the constraint set. There is no projection. And so if we run Frank-Wolf algorithm, it can efficiently find a multiset of size d log 1 over delta over epsilon squared, such that first of all they span the whole space Rd, and then the inner product is less than epsilon with high probability. Okay, so I'm going to parameterize Frank-Wolf with epsilon and delta. So if I give Frank-Wolf the epsilon and delta, it's going to find a multiset of this size that I'm showing here, such that the inner product is going to be less than epsilon. Okay, so this is the subroutine that we are going to use in order to solve our problem. Now let's describe the algorithm. Again, initially, we are going to have all arms are going to be active, and in each batch, except for the last batch, we compute, say the JS batch, we compute the multiset from the active set of arms A given by Frank-Wolf. And what do we do for each batch? Well, we set the parameters of Frank-Wolf optimally, and as follows. So epsilon of the JS batch is going to be defined as the way that I'm showing here, and delta is going to be overall batches is going to be constant. It's going to be 1 over k t squared. Okay, so what does it do when we run Frank-Wolf? It's going to select a set of arms, right? N arms. Once the set of arms are selected in the batch, we are going to execute them, see the result, and then we are going to run the least square estimator in order to find delta hat. And then we eliminate any arm that is suboptimal with respect to the best arm. And how do we define suboptimality? It's going to be basically 2 times epsilon j, the same epsilon that we use for Frank-Wolf. And again, for the last batch, we pull the we pull the active arm with the largest dot product, inner product with the last eliminated theta hat. Okay. So the regret of the batch arm elimination algorithm that for the stochastic linear bandit with k arms is going to be again bounded by t to the 1 over b square root of the expression that you see here. So again, if we set B to be on the order of log t, t to the 1 over b is going to be a constant. And it almost matches the fully sequential setting of grid bound, which is basically square root of dt times log k. And here, I only talked about finitely many arms, but the idea can be extended for infinitely many arms. And the only difference is that we have to construct what is called the epsilon net, and then among the centers of the epsilon net, we run Frank-Wolf over them. It's we get basically almost exactly the same. So again, from t iteration, we got to, from t interaction with the environment, right? We got to log t interaction while keeping the regret similar. Okay. So far I have talked about UCB and arm elimination, but another very popular policy for bandit setting is the Thompson sampling, which is also known, in different fields like posterior sampling or probability matching. So let me actually explain also Thompson sampling and how we can parallelize it. And here is basically the skeleton of the Thompson sampling. It keeps beliefs about the parameters of the arms, like the mean values, and updates them once new observations become available. So Thompson sampling in each round selects an arm with the posterior probability of being the best. Okay, so let's in this figure, let's say that these are the probabilities assigned to each arm, and then each arm has a probability of being the best arm, right, based on these probability distributions. So Thompson sampling is going to select an arm with that probability, right? So this randomization step is the way that Thompson sampling explores the environment, right? It adds randomness. And as we select an arm, more and more, the posterior distribution is going to concentrate better and better around the mean value, right? And we become more and more confident. But you might actually say, well, how can I compute this the probability that an arm is the best arm, right? So it seems like this is not a very simple problem, but there is a very simple way to realize Thompson sampling as follows. So let's say d sub a at time t indicates the distribution associated with arm A at time t. And at each round, what we do is that we sample each arm independently according to d. Okay, we get one sample for each arm according to their distribution, and then select the arm with the largest theta, the realization. Okay, so this is exactly the probability, if and this is exactly the probability that the arm is going to be the best arm. And once we observe the reward of that arm, we use the Bayes rule to update the distribution. Now, immediately you say that, okay, finding the Bayes, like the posterior, is not such a simple task. And because of the Bayes rule, we usually instantiate Thompson sampling with distributions for which computing the posterior is easy, such as Gaussian beta, etc. Okay. Now let me just explain how we parallelize Thompson sampling. Here, so for each arm, let's look at the JS batch. Batch Thompson sampling keeps track of the number of times the arm A has been selected so far. So initially, all the arms are going to be set to 1. So for each arm A, at the beginning of the batch, the number of times that it has been selected is going to be between two consecutive powers of 2, right? So now assume that a new batch starts at time t. So here within this batch, Thompson sample, batch Thompson sampling samples arms according to the prior distribution up to time t-1. So this is going to be d sub a of t, and selects the one with the highest value. Okay, so but because we do not immediately observe the reward, we do not update the distribution, and we continue selecting until the number of times an arm is selected reaches a threshold, right? So each arm has a threshold, how many times it has been selected. It is a power of 2. And once an arm reaches this threshold, we query all arms and update the posterior distribution of all arms selected in the batch. And then what do we do with the threshold? Well, we double that threshold. Okay. So this doubling trick is basically, very reminiscent to the halving trick used in the pure exploration settings for the best arm identification. So now, since we're using the posterior distribution, we should, choose a probability distribution for which calculating the posterior is easy. But the results that we are going to show are worst case. They do not depend on the real distribution of the rewards. Okay, so it's not a Bayesian setting. So one such distribution is the beta distribution. And for the ease of presentation, let's consider the simple Bernoulli multi-arm bandit. So because of the conjugacy, property of beta distribution, it is very easy to update the posterior distribution given the observations. So here we, initialize all arms with beta 1 and 1, which is a uniform distribution, and then update the posterior distribution by the number of successes and failures during the batch as follows, right? So SA is the number of times arm A was selected by, time t-1, and it was successful. The reward was 1. FA is failure; it was not successful. And then the posterior distribution is very simple. It's a beta distribution where we plug in SA and FA. And this can be easily extended to general reward distribution, supporting on 0, 1, not only having the value 0 or 1. And in order to do that, when a reward between 0 and 1 is observed, we flip a coin with the bias of the reward and update the beta distribution according to the outcome of the coin. So what we can prove is similar results, where we show that, again, we obtain the log T problem-dependent regret with basically log T rounds of interaction. And this, again, matches the lower bound about the regrets, right? So this is a simple way to parallelize Thompson sampling. And, for the contextual bandit, I don't know how much time I have.
So you have like 5 or 6 minutes, and then
okay.
We can start.
Sure. Okay. So, we can basically use the same result, a policy. So here, for the linear contextual bandit, we assume, Gaussian priors and Gaussian likelihood functions. But again, I should highlight that the analysis and the corresponding regret bounds hold irrespective of whether or not the reward distribution matches the Gaussian priors or, Gaussian likelihood functions, similar to the multi-arm bandit setting that we discussed before. And then, we can construct action context matrix, and very similar to what we did before, we can obtain the empirical mean as follows. And so mu hat, the empirical mean, is going to be, we can estimate it. So note that here we only consider the rewards of arms pooled in the previous batches. We do not, in order to estimate mu hat, we do not look at the rewards in the current batch. And, the strategy is similar, right? At each round, at each step T, within a batch, batch Thompson sampling generates a sample mu hat tilde, and plays an arm that maximizes the inner product between the context and mu hat tilde. Okay, and then because it's a Gaussian distribution, the posterior is very easy to update, and we use the same doubling trick. So what do we get? We can prove that the batch Thompson sampling achieves the same regret as the fully sequential Thompson sampling, while having log t number of batches. The other thing is that if you see here, you see that the regret is going to be d to the 3/2, and but the optimal regret, we know that it is only d times square root t log 1 over delta. D is square root t. So so in that respect, Thompson sampling, even the sequential one, is suboptimal, and it seems to be actually unavoidable. And Bayati and Hamidi showed that there exists indeed cases where Thompson sampling gets exactly this regret. And so finally, what I wanted to talk about was, talk about the most general setting where the reward is a non-linear function of the context. Okay, for instance, the reward is 10 times smoking squared plus 5 times diabetes cube plus 3 times, square root of the blood pressure. So what should we do now? Right, and so in any round t, the reward is generated from an unknown function plus some additive noise, and we make no assumption about the reward function other than it is bounded, and we define regret as before. So can we solve such nonlinear contextual bounding problems? And if you look at this setting, it is a you have a nonlinear function, so you can immediately think of approximating this nonlinear function. How can we do that? Well, in order to reward the reward function, we can leverage the representation power of deep neural nets. So in particular, we assume that we have a fully connected neural net with depth L and width M for each hidden layer, and we use the ReLU activation function, and we put all these weights into this huge matrix theta, and given an input x, right, and the set of weights, neural net is simply mapping x to a value, right? Nothing but that. Okay. So at a high level, we use neural net to learn the unknown function h, and then use the UCB strategy to guide the exploration. So to train the neural net, we have to use gradient descent, and to explore, we need to come up with new confidence bounds. And so within each batch, neural UCB basically receives the context vector and computes the UCB estimate of the reward function, as I'm showing here. Like the classical UCB strategy, we compute the upper confidence bound, where the first term is the mean value, using the current set of weights, set of weight parameters of the neural net, and the second term is the variance. And here G is the gradient of the neural net evaluated at theta B, and Z is the covariance matrix that is updated within each batch. And note that the parameter of the neural net is not going to change within the batch. And what do we do? We use exactly the same strategy. We select the arm that maximizes the optimistic reward, and then the update the covariance matrix. Okay. So once the batch finishes, so the rewards are collected during each batch. We observe the reward. So we use all the rewards and contexts seen so far as the input of the neural net for training, And in order to establish our theoretical results, we consider, symmetric initialization, where we ensure that, the weights are set in such a way that at initialization, the function does not have any bias. And then, we use a regularized quadratic loss for gradient descent. And that gives us, the new parameter theta b. So, and then how do we choose the batches? Well, here we look at the determinant using the same idea that, when the determinant is greater than 2 times that of the determinant of, previous batch, we, we finish the batch and we end the batch. So it's the same doubling trick strategy. And under the over-parameterization setting, meaning that the width is very large, and with d tilde log t number of batches, d tilde is the effective dimension, and with high probability, we basically get the regret that is d tilde square root t. And that turns out to be, basically optimal, right? So we know that the number of batches should scale like d log t log t to achieve square root t recurrence, even for the linear batch. Okay, so there are some empirical results that maybe we don't have time to show, but it basically shows that this batch neural UCB achieves the lowest regret, while having the execution time is going to be lowest among all other methods, because because of this batching, that we don't have to update the parameter of the neural net within the batch. Only when the batch finishes, we retrain the neural net. So if you have not been convinced that going from t iterations to log t iterations, like exponential speed up, is very important, let me actually run this clip.
The screen. iPads, which are made by Apple, have artificial intelligence in them that allow things to be viewed through 3 dimensions and logarithms. Logarithms, I don't understand it all either. It uses artificial intelligence for their logarithms to create what they believe is happening.
So I guess this gentleman is confused between algorithms and logarithms, but it seems that logarithms are very important for AI. Anyway, so in this talk, I try to present some other results about batch bandit, but in the same spirit, one can look at other optimization and learning settings and investigates whether semi-adaptive algorithms and policies with the same benefits exist. And we actually done it for a number of problems, for some modular functions, for online learning, and recently for RL. So thank you very much.
Thank you, Amin, for a great talk. So I'd like to open the floor and see if the audience have any questions. So please feel free to unmute yourself to ask your questions, or just write it in chat, and I'd be happy to read that out loud. So perhaps I can start with a few questions. So if I understood it correctly, the number of batches B for the settings that you talked about in your presentation, that depends on the time horizon capital T, right? So I mean, there are some previous results that if you don't know capital T, you can use, for instance, I don't know, adaptive parameters or doubling trick to deal with that. But can we sort of use a similar idea here if you don't know T?
That's a good question. I don't know, actually. I don't know whether or not, if you don't know T, the horizon, does it affect you or not? Maybe it doesn't, but that's a very good point. I don't know. Yeah.
Well, thank you. So perhaps I can ask another one while we are waiting for our audience. So my question is related to the least square estimator. And I mean, obviously there is an inverse of a matrix involved, and should we be concerned with its invertibility or?
Right. So basically, what I showed was the unregularized version.
I see.
But then what you can do is that add lambda times identity, and then you can get basically the same results.
I see.
And you know that, at
Makes
that,
sense.
yeah.
All right. If there is no question, then we'd like to thank our speaker, Professor Amin Karbasi, again for his great talk. And yeah, I'd like to thank the audience as well for attending.
Yeah, thank you very much for the invitation again.
Yeah, thank you.
Thank you, Amin.
Have a very good day. Bye.
Bye. Bye.